Megan's professional background includes a Bachelor's of Science in Atmospheric Sciences from the University of Kansas and a Master's of Science in Hydrologic Sciences from Boise State University. So you'll learn what all that means. And she has previously held positions in the U.S. Geological Survey as a lab tech and the U.S. Peace Corps as a math and science teacher in Tanzania. She's done a lot of other things, including working at the Kansas Department of Health and Environment and the City of Lawrence as a water quality lab technician. And she currently works on water quality standards with the Environmental Protection Agency. Her hobbies include reading, binging on Netflix, cooking, hiking, camping, backpacking, and sitting in front of fires. So today you're going to learn why she's a scientist and why she's also a real person, just like all of you. And she's going to focus her talk on climate change. Now, before we get into her talk, really quick, I just want to talk about, just a sec. I'm happy to turn them on, Mr. Espinoza. I don't know how.
Okay, I'm trying to figure that out right now.
I'll
message you when I figure it out. Thank you.
Okay, sure. Okay, so before we get into that, we're just going to touch on what makes up an educated question. So scientists like Megan become scientists because they're wondering something and they ask questions about it and it leads them to wondering something else. And then they can make awesome new discoveries. So an educated question is really anything you can come up with that might lead you to new knowledge. So as Megan is talking, I want you to come up with some educated questions. That means anything you're wondering about. And at the end of her talk, we're going to have some time for question and answers. So write down all your questions and we'll get to ask them after she's done. So Megan, go ahead and take it away.
Hello, as Leah said, my name is Megan. I work for Environmental Protection Agency, or EPA, in Region 7, and I'll show you where that is in a second because I'm in Kansas personally. And I'm going to be talking about how climate change impacts hydrology. So first off, let's talk about my background studying climate change. So this is an image from my master's thesis from Boise State University. And what I was doing was looking at how land cover change, in this instance, how cutting down trees or removing trees in this area in Mozambique would impact different weather patterns and rainfall. So I think one of the biggest things I learned from my master's program was I worked with a group of different climate change researchers who all worked with different climate models. And they each have their own way they work. Every climate model is a little different. This is the weather research and forecasting model that I used. And so learning about how their limitations and advantages and all these different things, how you can interpret this model output, was a really big part of what I learned in my master's thesis. Nowadays, though, I work more on the policy side of things. So I don't actively work in research, but what I do is look at the research that's being done and try to apply it to what I'm doing, which is a water quality standards coordinator here in Region 7. So that covers Nebraska, Iowa, Kansas, Missouri, and then any tribal areas within that region. So what I look at nowadays is we work with the states and the tribes to come up with water quality standards to help protect health and safety and also aquatic life in these areas. So like I said, nowadays more the policy side, but I still have to keep in touch with what's going on in the research side to make sure that we understand where everything is going and how things are changing in our environment. So let's talk about what hydrology is. Basically, hydrology is the movement of water over the earth. So we're looking at the whole entire water cycle, although most of the time hydrologists are really concerned with what happens after the precipitation hits the ground. But we do have to consider every portion of the water cycle to learn about hydrology. So you can see here we have things like, precipitation, evaporation, evapotranspiration, which is evaporation and then transpiration from leaves. So we have water leaving the ground plus water leaving from plants and then we'll have it come down as precipitation, either as snow or as rain or other precipitation, and then it'll accumulate in the rivers, and some will go down into the ground. And so really we're looking at where that water is, how long it's staying there. And then there are other portions of hydrology like water quality, like what things are contaminating the water, and such as that. So if I could ask you all a question, what do you think is a role that climate change could be playing on something like evaporation? Anybody have any ideas? Do y'all know what evaporation is?
Megan, that on Zoom they get very shy.
Yeah.
So you guys feel free to just unmute yourselves and answer, because in class they're not shy like that. When they get on, they do get very shy. So
I understand.
I'm encouraging you guys, just pretend that we're in class. And if you've got any ideas, feel free to jump in.
It encourages less water to come.
Okay, so evaporation depends on heat that's heating up the water molecules, and then they evaporate into the air. So if we're adding more heat, what do we think will happen?
More evaporation.
Yeah, so that's exactly what's going on, is if we're adding more heat, we're getting more evaporation. And then there's a lot of other issues in the water cycle that are changing as well due to climate change, just because these are very complex systems. And so we're actually changing the way weather patterns work, which is kind of crazy to think about. And the other thing I wanted to point out here is that this chart and a lot of charts like this don't really include the human component of the hydrologic cycle, but we really impact the hydrologic cycle a lot, like with dams and use for farming, things like that. So we're a big component in this as well. So that's something to think about too. Okay, and then I have quite a few charts and graphics from a report that I use the same one throughout all of it. So I wanted to give you a citation, and I shared these links with your teacher. So hopefully that gets shared around. So you can look into this. It's the 4th National Climate Assessment Volume 2, Impacts, Risks, and Adaptation in the United States, Chapter 2, Our Changing Climate. And there's several authors involved. And there's a lot of coordinating authors from the National Oceanic and Atmospheric Administration. And anytime you get a big report like this on something that's very broad, you're going to get a lot of people working on it, because we have people who are experts in different areas. And again, this is all very complex information. So we have to have a lot of people working on it and making sure we understand the best of each area of science. And then we have a few more citations for technical contributors. So we have different universities involved as well. So a lot of people working on this. Okay, so I like to start my talks with the key points so you can keep them in mind as we're going through. So key takeaways for climate change and hydrology. The effects of climate change on hydrology are dependent on how much CO2 is in the atmosphere. So this is something that's really difficult to predict because it depends on human behaviors, right? So we have a really hard time determining or trying to figure out how much CO2 will be in the atmosphere in the future, because it really depends on, governments, the entire globe of people and what they want to do with CO2, new technical advancements, things like that. So we come up with different scenarios to look at what could potentially happen if under these different CO2 scenarios. The next big thing is hydrology and climate change in general are dependent on your regional weather and climatology. So, if you think global warming, sometimes people think, oh, it's just going to be warm outside all the time, which is not what ends up happening. We have, again, these complex systems that are working together. So we kind of have to piece out what's going on at each individual location and what really impacts you. So I tried to pick out some things today that will affect you more in California than me here in the middle of the country. And then overall, heavy precipitation events will likely become more frequent and or more intense. So we're talking about really big rainfall events where a lot of rain comes down at once. And then, however, surface soil moisture is likely to decrease across the United States. So first, we're going to talk about climate change scenarios, and you maybe have learned about this before, but I wanted to make sure we kind of go over it again, just to make sure we are on the same page. So on the left here, we have a graph that shows global carbon emissions from the years 1900 to 2100. And you can see on the y-axis here, fossil fuel carbon emissions in gigatons of carbon per year. So this black line is what's been observed. So these are based on observations that were made. And then these lines here are based on predictions of what might happen with CO2, just different scenarios of things that we want to look into. So this highest scenario, we're saying we're just going to keep dumping CO2 in the atmosphere, and this is what's going to happen. Then we have a scenario that's the lower scenario, where at some point in the year 2050, we curb off emissions and they drop off. And then we have another scenario where emissions drop off right away. So what people have done is taken these different scenarios and put them in different climate models. I've got to move my chat box here. So we have these different climate models here. This is the output from different climate models. And you see there's a range here, and that's because there's a lot of different climate models giving different answers. And so there's some variability in the answers of how much we think the temperature will change. But if you notice, in all of them, we're seeing an increase in temperature. So that's something we are pretty sure is going to happen. There is expected to be at least a 2 degrees Celsius change in temperature based on the current climate emissions. But this could also go up as much as 5 degrees C by the year 2100. And so you can also see this green line here extends back here beyond the observed data. And so do the other lines, you just can't see them because they're back behind. But that's good practice in climate modeling, because you want to make sure that what you're modeling represents reality. So what you do is you model something that's already happened. And if your output looks like what was actually observed, then you can say, oh yeah, our model's working correctly. Now we can go into the future and predict what could be happening in the future. So that's one thing with climate modeling that's good to keep in mind, is that they do practice on things that have already happened to make sure that their results are reasonable. Okay, so now that we've gone over these different climate scenarios, we'll go over different effects on the hydrology in the United States in particular. So again, this is all from the same report. So we're going to be discussing the years 1900 to 2100. This is what the report covers. And then these different scenarios. So we have the higher one, and then the lower one, and an even lower. So first, let's talk about snow and soil moisture. So one key takeaway from this report was that surface soil moisture over most of the United States is likely to decrease, accompanied by large declines in snowpack in the western states and shifts to more winter precipitation falling as rain rather than snow. So this is really big in the western states in particular, especially with the snowpack, because, and I'll explain this in a little bit, but this is one way that our water is stored, is in snowpack. So if that's changing, that's going to be changing the timing of when we're getting some of this precipitation. So first, soil moisture and temperature. I mean, you can see up here we have the observed trends. So we're already seeing, and this is all temperature, and you can see gotta move my chat box again, it's all in the way. You can see the change in temperature down here. So this is just a change in temperature. That's what these maps are showing. So what's already being observed is an increase in temperature over most of the United States, although some portions are still showing a decrease. And then what's predicted to happen in the mid-21st century, so to about 2050, if we look at the lower scenario or the higher scenario, is an increase of about 2 to 3 degrees here in California, or in the higher scenario, it's even up to 3 to 4. And then in the late 21st century, so the year 2100, we'll have an increase in temperatures in the 3 to 4 range here and up to the 5 to 6 range here. So what's going on here is that an increase in temperatures will lead to increased evaporation. And if you're evaporating more off the soil, we're going to get drier soils. So that's just one thing that farmers will have to keep in mind when they're selecting what crops they can use or trying to understand what irrigation they should be using or what they'll need in the future. Okay, the next portion of this is the snowpack. So mountain snowpack acts like a reservoir for water, keeping it frozen form until the spring snow melt. So I have a water tower here because that's kind of what's happening with the snowpack. So imagine you have rain or precipitation falling as rain on a mountain. What's going to happen to that rain when it hits the mountain? Anybody have any ideas?
It's gonna like evaporate into the soil.
Yeah, it can evaporate, and then it can also just run downhill. So where our water isn't being stored there for us, it's just moving around. But what happens if it falls as snow?
It stays in place on the snow.
Yeah, it just stays in place. So that's what's happening in a lot of the Mountain West, is that the precipitation is going to be falling more as rain more often than it is as snow. So it won't be staying in place, and then it will also melt earlier in the season. And both of these things are huge for water law in the West, because we have all of these rights that are based on the timing of snowmelt and based on when people can access water and how much water there is. And it's usually based on the spring snowmelt. So all of these things might be changing in the future. So that's just something we're going to have to keep in mind. Okay, next thing, effects on weather patterns. So as I was saying, all of these complex systems are going to be changed differently by climate change. So one of the things that will be different are weather patterns. So we got some bullet points from our report again. Human-induced change is affecting atmospheric dynamics and contributing to the poleward expansion of the tropics and the northward shift in the Northern Hemisphere winter storm track since 1950. So I'll explain all of that in a little bit. We'll get there. In the future, Atlantic and Eastern North Pacific hurricane rainfall and intensity are projected to increase, as are the frequency and severity of landfalling atmospheric rivers on the West Coast. So this might be something you've heard about a lot recently, are the atmospheric rivers. I know when I was living in Idaho, we had a really intense season one year where it just kept snowing and snowing and snowing because of atmospheric rivers. And then lastly, observed increases in the frequency and intensity of heavy precipitation events in most parts of the United States are projected to continue. I'm sorry if you can hear my cat. She's very upset that I'm not letting her in my office. Okay. So if we're going to talk about the changes in weather patterns, one of the most important things to understand is what a jet stream is. So I found this video from Noah Sijinks that explains it really well. So just sit back and watch this for a second.
They travel about 110 miles per hour. In the winter, what is the jet stream? Jet streams are bands of strong wind that generally blow from west to east all across the globe. Jet streams form when warm air masses meet cold air masses in the atmosphere. Air masses have different temperatures because the sun doesn't heat the whole Earth evenly. Areas near the equator are hot, and areas near the poles are cold. The warmer air rises up in the atmosphere while cooler air sinks down to replace it. This movement causes an air current. These air currents are high in the atmosphere. On average, they travel about 110 miles per hour. In the winter, when the temperature differences between warm and cold air masses are more dramatic, jet streams can go much faster, 250 miles per hour or more. No matter the season, the primary jet streams only travel from west to east because of how Earth rotates on its axis. Jet streams are located in the middle and upper parts of a layer of the atmosphere called the troposphere. This is the height in the atmosphere where airplanes fly as well. That means airplanes can fly in the jet stream, especially when they're headed in the same direction the jet stream is blowing. This is why an airplane flying from west to east can make the trip faster than an airplane traveling the same route from east to west. Jet streams can also affect our weather by impacting temperature and precipitation. Some weather systems ride the jet stream across the country. Or, if the weather system is far away from a jet stream, it might stay in one place, causing a heat wave or a flood. Monitoring jet streams can help meteorologists determine where weather systems will move next. This is important because the path of a jet stream can change quickly, taking storms in different directions. NOAA's GOES-R series satellites use infrared radiation to detect water vapor in the atmosphere. With this technology, meteorologists can monitor the location and activity of the jet streams. The GOES-R series satellites can give up-to-the-minute reports on where jet streams are in the atmosphere and where weather systems might be moving next. Find out more about Earth's weather at NOAA SciGIS.
Okay, so one of the big things there to keep in mind is that what he mentioned about the air masses, where you have warm air masses coming together with cold air masses. What's going on right now with climate change is that the polar air masses are getting warmer than they were before. So our jet streams are kind of changing direction, and they're not changing direction, excuse me. They're changing how fast they're moving. They're changing how far north or south they are. So we'll look at this person next. So this is Jennifer Francis from Rutgers University explaining kind of what happened this winter. If you remember Texas getting all that snow, that can be due to these changes in the jet stream as well. That events like that are more likely to happen with climate change going forward. So here is an interesting video on that. And this is satellite imagery showing wind speeds.
The reason there are jet streams is because of the differences in temperature between different sections of the world. And that difference in temperature is what creates the force that drives these winds. As global warming is occurring, the Arctic is warming much faster than areas farther south. That means that this difference in temperature is not as large as it used to be. And so there's less force driving the winds of the jet stream. When the jet stream gets weaker, when those west to east winds slow down, the jet stream tends to travel in a wavier path. They're actually what create the dynamics in the atmosphere that creates weather patterns. Once those waves get quite large, then the weather patterns can become so slow that in effect they get stuck.
So I have another image kind of describing this, and
The reason there are
in a still. So this is what the stable polar vortex looks like when we don't have these waves she was talking about. And on the right here, we get these waves. So you get this cold air that can go much farther south than it normally would because the jet stream is weaker and kind of it drops down in further south than it normally would, which is how we ended up with snow in Texas this year. But in general, on average, what's going on is this track is moving further north because of the warming of the Arctic. Another big thing, as I mentioned, was the atmospheric rivers. So what's going on with an atmospheric river is you'll get this moisture from the tropics that comes up in a tail and hits the west of the United States, and you'll get a lot of precipitation from these events. And so this is projected to increase because more evaporation over the ocean means that we're getting more water vapor that can precipitate out and turn it into rain as it hits the West Coast. So this image is a total precipitable water vapor. So this is satellite imagery, and it shows what it looks like when atmospheric rivers hit the West Coast. So this blue color is more moisture. So I find that one super interesting to see because it's very apparent what's going on, especially on the ground when you're getting tons and tons of rain dumped on you. Okay, and then overall, we can say that precipitation will be changing across the United States. And this one really depends on the season. So they've split this out into seasonal changes. And then this is the observed. So in California, you're going to have an increase in winter precipitation. And this is late 21st century, so 2100 RCP 8.5. And we're saying a change in percent of about 10% here in the winter. Spring is maybe a slight decrease, summer is a slight decrease, and fall is also a slight decrease. So all these things end up, so this is average precipitation overall, but next we're going to talk about big precipitation events, which act differently than, you know, which is different than the average amount of precipitation over the entire year.
Hey, Dr. Maksimowicz?
Oh, I'm not a
Forgive
doctor,
me if
but
I'm
yes.
not. Oh, yes. Oh, well, that's true. Would it be okay? Because these are sixth graders, so this is pretty high level for them.
Right.
So would it be okay if we stopped here and there with some of these graphics and just let them ask some questions, maybe make some sense of it in their own heads?
Yeah, and I really
so
this is the last graph. So if anyone has any questions so far, let me know.
Awesome. Okay, thank you.
Any questions so far? No? Okay, so this is the last graph we have, which shows heavy precipitation events. So that means that these are the events where the most rain falls. So in our observations, we see that 1901 to 2016, and then they split it into 1958 to 2016 to see how much of a trend we're seeing. And we are seeing an increase in these heavy precipitation events. So they're happening more often and they're more intense. And that's what we're going to be seeing into the future as well. So in the higher scenario, we're going to be seeing more precipitation events, and they're going to more heavy precipitation events that are occurring more often and having more intensity. Any questions there?
Can you relate that to the drought that, the tendency towards droughts that we're seeing in California? Because
yeah,
because here, that's what we experience. Like, we haven't experienced the increase in precipitation here necessarily. Right. So can you help us understand that?
Yeah, so that is one of the parts that's most confusing, I think, about understanding hydrology changes, is that these are just the heaviest events are becoming heavier. But if we go back and look at this slide, on average, the only time we're increasing precipitation is in the winter. Otherwise, we're decreasing the total amount of precipitation. So when you do get rain, it's going to be more intense, but overall, you're going to have less. Does that make sense?
Totally. Does that make sense, you guys? Yeah, thanks for clarifying.
Yeah, no problem. Okay, and then the other big issue you have on the coast is sea level rise. So we've already seen global sea level rise has risen about 7 to 8 inches since 1900, with almost half of this occurring since 1993 as oceans have warmed and land-based ice has melted. Relative to the year 2000, sea level is very likely to rise 1 to 4 feet by the end of the century. And then the other big thing to keep in mind is that regional changes in sea level rise and coastal flooding are not evenly distributed across the United States. Ocean circulation changes, sinking land, and Antarctic ice melt will result in greater than average sea level rise for the Northeast and Western Gulf of Mexico under lower scenarios, and for most of the US coastline other than Alaska under high scenarios. So what they're saying here is just because if we get a 1 to 4 foot sea level rise in the US, that doesn't mean that all areas of coastline will have the same amount of sea level rise. And so that's one thing that's really difficult to determine because it depends on a lot of different things like the ocean circulations. So in the same way that we have jet streams in the air, we have circulations in the ocean where we have warm water moving in currents. So one of the things you can look at is this sea level rise viewer, and I picked an area close to you. So here's East Palo Alto and Bear Island, and these areas in the blue are areas where this is with 3 feet of sea level rise. So you can go to this viewer and check and see. So this is one of the worst case scenarios that we're predicting by the end of the 21st century. And this is a lower water depth and this is a higher water depth. So these areas would have some water, which is kind of scary when you think about it. So I did include ways that we can help adapt to these changes, because if you just think about the sea level rise, that part can get really, especially if you're in a coastal area, that part can get really scary. So what can we do? I've included here planning for climate change adaptation. This is a link that communities can use. So it's more based for cities and things like that. So they can try to determine what's going to happen in our area. Like, are we going to experience drought, or are we going to experience more flooding events? Are we going to experience a change in timing of the water and things like that? And they have a bunch of scenarios where they have listed out how to help prevent or adapt some of these changes. So that's there on EPA. ARC-X is what they call it. And then we also have a climate.gov toolkit that also has a bunch of steps for adaptation. So it kind of takes these communities like city leaders through different things that they can do to be adapting for the future. And one of these things they have are case studies. So I picked a case study near you. So to date, more than 20,000 acres of wetlands in the San Francisco Bay have been restored to tidal action after conservation groups obtained land and breached historic levees. In many cases, waters are flowing over these historic marshlands for the first time in over 100 years. Sonoma Land Trust and its partners continue to work on protecting and restoring the puzzle pieces of land across the region. Their goal is to connect a healthy watershed to a thriving tidal marsh ecosystem, one that will buffer people from the impacts of climate change and sea level rise well into the future. As Meisler and others face the unprecedented threat of sea level rise, they are choosing unprecedented strategies to conserve habitat and biodiversity. Oops. Okay, so in this case, they're preserving tidal marshes. And so what that means is that these are marshlands that are outside of the coast. So if you get like a big surge of water that hits the marsh, it's gonna kind of act as a buffer or slow down that water. So by the time it hits the coast, it's not as big of a problem, if that makes sense. So these are just some things that we can all be working on to help adapt to these changes in the future. And with that, are there any questions?
How come the sea level is rising when it's getting warmer and
Yeah.
things like that?
So sea level is rising because of ice that's melting, and it's due to ice that is on land bases. So if you think of a glass that has ice in it, if your ice melts, do you think the level will rise at all? So that's a trick question. It turns out as the ice melts in your water level will stay the same. However, if you put an ice cube on top of your cup or on a surface and that melts, then you will have a higher level of water. So what we're concerned with is ice that's on mountaintops or on land surfaces. And then once that ice melts, it'll flow into the ocean. And that's what's causing the sea level rises. And there's a couple other issues too with like expansion of water as it gets hotter, but that's the big issue. Any other questions?
Yeah, I was wondering if you could explain why the temperatures near the poles are increasing faster than those nearer the equator.
Yeah, that's a good question. So in general, I'm not sure if I absolutely know why. I should look that up. But in general, temperatures are changing differently all around. So nighttime temperatures are increasing more than daytime temperatures, things like that. So it just depends on how the sun is hitting the earth. So I think because our atmosphere is surrounding the whole globe, and that's what's causing the temperature to increase, that increase is more impactful in areas that don't already get a lot of sunlight, if that makes sense.
I just looked it up, and this may be wrong. This may be wrong, but it says, because that's a really good question. I was wondering that myself. It says the vapor is a big part of the amplification story in the Arctic because there's more water vapor, I guess. And so it makes sense to you?
Yeah, that would make sense. And that, yeah, so the way that greenhouse gases work is that if we have CO2 and also methane and also water vapor, all these things are greenhouse gases and they'll all interact differently. And water vapor is an interesting one because it's temperature dependent. So we already have quite a bit of it around the tropics. And if we're increasing the temperature in the Arctic, that means that more water vapor will be there. And so that will end up warming more. So maybe that is it. Thanks for the lookup.
So Megan, I have a question for you. Looking at these potential models, are those taking into account the developments and things we're trying to do to prevent climate change, like reducing emissions and putting less pollutants into the air?
Yeah, so that's why on this scenario, there's a decrease because and this one is a big decrease because this is saying, okay, if we all work together and start really curbing emissions by the year 2050, this is what we'll be seeing as a decrease in emissions. And I'm not 100% sure how they determined what exactly those emission changes would look like. But this is just based on different scenarios that they thought could happen.
Yeah, it's interesting to me that middle one, it goes up for a while, then it goes down, probably because of, mitigations and adaptations, and then it levels off. So yeah, maybe it's like when we finally get to the point where we've done all the adaptations and mitigations, then it levels off.
I'm thinking it's one of those things where they decided it wouldn't get much better than that for some reason. I don't know.
I think we've got time for maybe one or two more questions. Students, if you have anything else you'd like to ask Megan, and you can also ask her about her life or her career as a whole, anything you'd like.
Megan, can you tell us about the research that you did when you were doing, like, what do you do as a scientist on a daily basis? Like, what's your life really like? Paint a picture for the kids.
So when I was working on my master's thesis, every day was just, well, mostly when you're working on your master's thesis, every day is trying to figure out what you're doing because it's the first time you're doing a big research project with just the help of someone else. So I was learning how to use the model. I went to a couple of trainings to learn how to do that. I was learning how to program to figure out how to deal with this model output. And then also just looking into a lot of a lot of research. So reading a lot of scientific papers and discussing them with fellow grad students and figuring out what it means and what would be interesting to look into. So we knew going into this that climate change, or that weather patterns can be impacted by land cover change. And we knew that the tropics would be an interesting place to study this because of the high rates of transpiration and evaporation from the tropics. So that's why we ended up studying this here in Mozambique. And they have a lot of land cover change because they have a lot of deforestation going on. So these are all things we wanted to look into and see how it could affect outcomes of weather modeling. So one thing we determined from this is that the land cover inside the weather models is really important. And that's something that doesn't always change as often as it should, maybe, because it's hard to keep up those data sets up to date. So that was something that was super interesting. And then now that I'm working on standards, most of what I do is review different laws and different cases going on in different, it's a lot of reading and editing guidance for states, which is interesting as well. I also just started this position, so I'm very new at it.
I have a question. When did you start getting into climate change and liking it?
I didn't catch that. What was that?
When did you start your research on it? I don't know how to say it.
When did I start this research, or a different, all of it?
When did you start doing it? How old do you think you were?
Okay, yeah, so I would say I started helping with research projects in my undergraduate. So that's when I was in college. So I was, 18 or 19. And then I worked in a lab after that. And so I helped out with research as well. But then I didn't really write my own research or really come up with my own research problem or really dive into things myself until my master's program. And then I was in my late 20s. So yeah, and nowadays, like I said, I mostly just look at other research and try to apply it to what I'm working with.
Megan, did you know you wanted to be a scientist looking at our climate when you were a little kid?
So when I was middle school age, I super wanted to work for NASA and wanted to go to space or something like that. So I knew I wanted to work with science, but I wasn't sure what exactly I wanted to do. And then I kind of ended up in climate because it affects everything right now. So if you're studying anything to deal with the earth, you realize that just about anything you're studying is going to have to do with climate change. And I think it's a really important area, and I really care about water. And that was the other big issue, is that after I went to the Peace Corps and really dealt with a lack of water and water quality and issues like that, I realized it's something I really wanted to work on and make sure I could help improve in some way. So that's how I ended up more on the water quality side of things.